The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. All right, so today we're going to go on to section 9.4, which is multiplying and dividing radical expressions. So let's go ahead and get started here. So let's say we've got the square root of 5 times the square root of 15. Okay, just like we can take a product inside a radical and pull it apart into different factors. So for instance, let's say we have the square root of 75 equals the square root of 25 times 3 equals the square root of 25 times the square root of 3. So just like we can go that direction, we can also go back the other direction. So we could take this and write it as the square root of 5 times 15, which then would be the square root of 75. Okay. We can put them together, take them apart as long as they have the same index and they all result in real answers. So now that I've got the square root of 75, I could go back and pull it apart this way and have 5 square roots of 3 as the final answer. So I can go from here to here. Now, there is a shortcut, or I should say a shorter way of doing that. Let's see here, let's get rid of this. We could, from here, write this as that. Oops, I don't want the square root symbol there yet. And then move these together. In other words, rather than put the whole thing together and pull it apart again, we could just pull out the piece that we need here to put together with the piece there, etc., etc. Either way, we get a final answer of 5 square roots of 3. Okay, let's say we've got -3 times the square root of 11 times the square root of 33. We could break that apart as -3 times the square root of 11 times the square root of 11 times the square root of 3, because this would equal that. Okay, then we can come back and say, well, that would be 11. The square root of 11 times the square root of 11 would be 11. So we've got -3 times 11 times the square root of 3, or -33 square roots of 3. So we can pull this apart, get this, put it together with that to get something nice outside. Okay, let's say we've got 2 cube roots of 16 times negative the cube root of 4. Okay, well, 16 is 4 times 4, or 2 times 2 times 2 times 2, or 2 to the 4th power. And 4 is 2 times 2, or 2 squared. Okay, so we could take this whole thing and rearrange it as 2 times -1, that -1 coming from here, times the cube root of 16 times the cube root of 4, okay, which is -2 cube roots of 2 to the 4th times 2 squared. Where am I getting these from? I'm getting them from over here, okay, which is -2 cube roots of 2 to the 6th power, okay, which is -2, and then what? The cube root of 2 to the 6th would be 2 to the 2nd power. So I've got -2 times 4, or -8. And the particular way that I pulled it apart, could have done it a different way. For instance, you could say that would be the cube root of 64, which is 8. And then you'd have, let's see here. Oh, the cube root of 64 isn't 8. Cube root of 64 is 4, which is that same 4. So again, there's a variety of ways that you can pull this thing apart or put it together, but you're wanting to find cubes so that you can uncube them. Okay, what about this one? The cube root of 3 times the cube root of 18. Well, that would be the cube root of 3 times 9 is 3 times 3 times 2. So what have I got there? I've got the 3 and then I've got the 18. Okay, but that's the cube root of 3 cubed times 2. Again, 3 cubed. The cube root of 3 cubed is 3, and then we've got the cube root of 2 left inside. So we're taking factors from different radicals that are being multiplied together and putting together the pieces that we need so that we can undo them and kick them outside. All right, what about this one? 3 times the square root of 8x times 2 times the square root of 2x cubed y. Okay, so I'm dealing with square roots, so I want squares. Well, this would be what? 3 times 2 is 6. Square roots of 16x to the 4th y. Again, where did I get the 6 from the 3 times 2? Where did I get the 16 from the 8 times 2? Where did I get the x to the 4th from the x and the x cubed and then the y? Okay, so I'm just skipping all the intermediate steps there. So now I've got 6 times, the square root of 16 is 4, square root of x to the 4th is x squared, square roots of y. So I've got 24x squared square roots of y, my final answer. Okay, I'm going to go back through this problem and show how I got from here to here, sort of doing it the drawn out longer way. So that would be 3 times 2 times the square root of 8x times 2x cubed y, which would be 6 times the square root of 16x to the 4th y, which again would result in that. Okay. Let's see here. We've got the 4th root of 2r cubed times the 4th root of 8r squared. 8 is 2 times 2 times 2, or 2 cubed. So this is the 4th root of 2 times 2 cubed times r cubed times r squared, which is the 4th root of 2 to the 4th times 2 times r to the 4th times r. Again, putting them together, raised to 4th powers and leftovers. So these are going to stay inside. This is going to be a 2 on the outside. This is going to be an r on the outside. So I get 2r, 4th roots of 2r. Oh, wait a second. Wait a second here. I messed up. How did I mess up? Well, let's look right here. That should have just been 2 to the 4th power. So that 2 shouldn't be there. Yep, sorry about that. Miscalculated. I need to slow down. All right. It says multiply and simplify. We've got 2 square roots of 7 times the quantity 3 minus the square root of 7. So we're going to distribute 2 square roots of 7 times 3 minus 2 square roots of 7 times the square root of 7. So this whole thing would be 2 times 3 is 6 square roots of 7 minus, well, the square root of 7 times the square root of 7 is 7. So that would be 2 times 7, or 6 square roots of 7 minus 14. The square root of 7 times the square root of 7 is, you could go the long way and say it's the square root of 49, which is 7. Or you could just say, well, the square root of 7 squared is 7. Okay. Negative the square root of 3 times the quantity, the square root of 7, minus the square root of 15. So we get negative the square root of 3 times the square root of 7, minus the square root of 3 times negative the square root of 15. This becomes negative the square root of 21, and then we've got a double negative here, so plus the square root of what? 3 times 15, but that would be 45, which would be the square root of 9 times 5. So negative the square root of 21 plus 3 square roots of 5. And let's see here where we are. How about, let's see here, this one. The cube root of 3 times 2 cube roots of 9 plus the cube root of 18. So the cube root of 3 times 2 cube roots of 9 plus the cube root of 3 times the cube root of 18. 9 is 3 times 3, or 3 squared. So this becomes the cube root of 3 times 2 cube roots of 3 squared, or 2 cube roots of 3 cubed, or 2 times 3, or 6. Okay. And the second one becomes plus the cube root of 3 times, let's see, 18 could be 9 times 2, or 3 times 3 times 2, 3 times 3 times 2, which is the cube root of 3 cubed times 2, which is 3 cube roots of 2. And so we end up with that lovely thing. And those can't be combined because they're not like radicals, so to speak. The first term isn't a radical at all. But again, what are we trying to do? We're trying to match the index. All right, now, this is kind of like foiling polynomials. It says, multiply and simplify. All variables represent positive real numbers. In case we run across any variables here. The square root of 2 plus 1 times the square root of 2 minus 3. So we're going to get 4 products. The square root of 2 times the square root of 2 minus 3 square roots of 2 plus 1 square root of 2 minus 3. Well, the square root of 2 times the square root of 2 is 2. And then we've got, let's see, these are like terms. Minus 3 square roots of 2 plus 1 square root of 2 would be minus 2 square roots of 2, and then minus 3. But those are like terms, so we've got negative 1 minus 2 square roots of 2 as our final answer. Let's see here. The square root of 3m plus the square root of 2n times the square root of 3m minus the square root of 2n. Do you notice anything special about these two groups in parentheses? It's a conjugate pair. We've got something plus another thing, the same something minus the other team. So this should be the difference of 2 squares. When we multiply it together, our middle terms should cancel out. Let's see what happens. Okay. So we've got the square root of 3m times the square root of 3m minus the square root of 3m times the square root of 2n plus the square root of 3m times the square root of 2n, and then minus the square root of 2n times the square root of 2n. Well, let's see here. This is going to give us what? 3m minus the square root of 6mn plus the square root of 6mn minus 2n. The middle terms cancel out. 3m minus 2n is our final answer. So this is the difference of two squares, but this is the square root of 3m squared, and this is the square root of 2n squared. So it doesn't quite look the same as we're used to from the past. Okay, how about this one? Let's see. The cube root of 3p minus 2 cube roots of 2 all times the cube root of 3p plus the cube root of 2. So this is not those conjugate pair factors for the difference of two squares. It's close, but not quite. So let's see here. We're going to get the cube root of 3p times the cube root of 3p plus the cube root of 3p times the cube root of 2 minus the cube root of, let's see, whoops. Okay. Let's see, we've done this one, that one. We're going to get minus 2 cube roots of 2 times the cube root of 3p, and then finally minus 2 cube roots of 2 times the cube root of 2. Okay. Well, let's see. Taking these first two and putting them together, we would have the cube root of 9p squared, and 9 can't be broken down into a cube, neither can p squared, so that's going to be stuck as it is, plus here we're going to have the cube root of 2 times 3, 6p, okay, and here minus 2 cube roots of 6p, because we've got the 6p there and the 2 outside, and then finally minus 2 cube roots of 2 times 2, or 4. And again, 4 can't be broken down into a cube. But these two terms are like terms. So we get the cube root of 9p squared plus 1 minus 2 minus 1 cube root of 6p minus 2 cube roots of 4. And even though there's a 1 implied there, I don't need to write it there because, again, it's implied. Okay, let's see here. What about the square root of 11 squared? Well, that would just be 11. What about the cube root of 9 cubed? That would be 9. But what about 2 square roots of 5 squared? That wouldn't be 2 times 5. That would be 2 squared times the square root of 5 squared, which would be 4 times 5, or 20, because that outside exponent gets attached to each factor, to the 2 and to the square root of 5. So be careful with that. Along those same lines, if I've got negative 3 cube roots of 10y cubed, and the whole thing is cubed, that's like negative 3 cubed, and then the cube root of 10y cubed, because this cube gets attached here and there. So I get negative 27, and then here those reduce out to 10y cubed, so negative 270y cubed final answer. All right, now let's go back to arithmetic for a minute. If you have the fraction -2/3, you can write it as -2/3 or -2/3 or 2/3. These are all equivalent fractions. However, someone way back when decided that we don't want to leave a final answer with a negative sign in the denominator if we can help it. So we would either write it here where the negative sign is out front of the whole fraction, or here where it's just applied to the numerator. But the idea being that with a fraction, we want the denominator nice, we don't want it negative, we just, nice and clean. Okay, now, let's talk about radicals. Let's say we've got the square root of 4/3. We could break that apart into the square root of 4 over the square root of 3, which would then become 2 square roots of 3. Well, just like we don't like to have a negative attached to the denominator, we don't like to have a denominator of a radical being a radical. In other words, we want to what we call rationalize the denominator. So we want to take the square root of 3, which is irrational, and turn it into a rational denominator. Okay, so again, it's called rationalizing the denominator. Now, the question is, what would we need to multiply it by so that over here in the final answer we'd get something nice? Well, if we multiplied by the square root of 3 over the square root of 3, the denominator would now be rational. Of course, in the process, the numerator becomes irrational. So it's not like we can necessarily make everything nice, but we make the denominator nice and push that irrational expression up to the numerator. Okay, so let's see here. Let's take a look at this example. We've got the square root of 5/3. The directions say rationalize each denominator. So I'm going to break it apart into separate radicals. I'm going to multiply by the square root of 3 over the square root of 3. So in the numerator, I get the square root of 15, or the square root of 5 times 3, and the denominator is rational. Okay, how about this one? The square root of 8. Oops, hang on. The square root of, come on now. Here we go. The square root of 8/7 equals the square root of 8 over the square root of 7. We're going to multiply by the square root of 7 over the square root of 7, which gives us the square root of 56 over 7. So we've rationalized the denominator. However, if there's more things that we can do, we need to also do that. In other words, we can simplify the square root of 56 because, let's see here, 56 is 8 times 7 or 4 times 2 times 7. There's a square, so 4 times 14. So we'll write this as the square root of 4 times 14 over 7. But the square root of 4 is a 2 outside. So we get that answer. Okay. Again, we rationalized the denominator, but then we went back and also simplified the numerator. So it's basically anything we've taught you, then we expect you to keep doing that in future problems. Isn't that fun? Okay, now take a look at this one. We've got 8 over the square root of 10. So I could multiply by the square root of 10 over the square root of 10, and I'd get 8 square roots of 10 over 10. Okay, so I've rationalized the denominator. But there's more we can do because we can reduce 8/10 to 4/5. So we get 4 square roots of 10 over 5. Now the square root of 10 cannot be simplified, so we leave it. Okay. How about this one? It says rationalize each denominator. Again, all variables represent positive real numbers. So we've got the square root of 15b squared divided by the square root of 5b cubed. There are a couple of different ways we can do this. I think what I'm going to do is I'm going to put these together first of all. So 15b squared over 5b cubed, both inside the same radical. Then I'm going to reduce, let's see, 15 over 5 is 3 over 1. And b squared over b cubed is 1 over b. So what do I end up with there? I end up with a square root of 3 over b. I haven't rationalized anything yet, but I've just simplified what's inside. So now I've got the square root of 3 over the square root of b. I'll multiply by the square root of b over the square root of b, and I'll get the square root of 3b all over b. So there you have that. Let's take a look at another problem. The square root of 9xy over the square root of 3x squared y. So again, I can put those together under the same radical. 9xy over 3x squared y becomes the radicand. We can reduce 9 over 3 is 3 over 1. X over x squared is 1 over x, and the y over y is 1 over 1. So the whole thing reduces down to what? 3 over x inside. Okay. Now, that's equal to the square root of 3 over the square root of x. I'll multiply by the square root of x over the square root of x, which gives me the square root of 3x over x. And I can't reduce anything any further. Okay, let's take a look at another example here. 11 over the square root of 75 s to the 5th power. That would be 11 over. Well, what I want to do before I rationalize the denominator, I'm going to see if I can simplify it, kick some things outside, which then will be rational and I won't have to deal with them. So let's see, this could be written as what? 25 times 3 times s to the 4th times s, okay, which would be 11 over 5s squared, square roots of 3s. So now that 5s squared outside doesn't need to be rationalized because it already is. So I'll come back and multiply, by, let's see, the square root of 3s, the square root of 3s. So my new numerator is 11 square roots of 3s. My new denominator is 5s squared times 3s, which is 11 square roots of 3s over 15s cubed. Let's see here. Okay. So I simplified that before I tried to rationalize it. Otherwise, I'd have to multiply everything by the square root of 75s to the 5th over that same thing. That works. You end up having to reduce it at the end. So it's like you can do it up front or do it at the end. How about this one? 13 over the square root of 32n cubed. So let's take a look at the square root of 32n cubed. That's 16 times 2 times n squared times n. And what I've done, I've kind of skipped some steps there, but I've broken it down into squares and leftovers. Okay, so the square root of 16 is 4. The square root of n squared is n. So the denominator becomes 4n times the square root of 2n. So now I don't have to deal with that whole 32n cubed. I just have to deal with the square root of 2n. So we'll go square root of 2n square root of 2n equals 13 square roots of 2n over 4n times 2n, which is 13 square roots of 2n over 8n squared. Now, if the 13 outside and the 8 outside in the denominator could reduce, I would, but they don't. So we're done with that one. Okay. Let's see here. What about this one? The square root of x times x plus 3 times the square root of x cubed times x plus 3. Keep making my radicals longer than they need to be. Well, that would be the square root of x to the 4th times x plus 3 squared, which would be what? X squared, x plus 3, or x cubed plus 3x squared. Okay. All right, that's all I've got for you today. So section 9.4, multiplying and dividing radical expressions, which includes rationalizing the denominator. And I'll be back this afternoon at 1:15 with an office hour should you have need of me.